Okay, so today's notes on 8.2a is a study of graphing just the basic trig functions. So today we're going to talk about even and odd trig identities, which I'm going to introduce some identities today, the even odd identities. So you'll want to add those to your index card as well as your note page. So today's essential question, why are some trig functions even while others are odd? Explain or illustrate. So that's my overall goal for you, is to be able to tell me why, not how, not which ones are even and which ones are odd, but why are some of them even and why are some of them odd. Whether you have to draw a picture to explain it or you can tell me verbally, that does either way. So let's start with an investigation, just to lead you into what I would like you to think about. So here's the investigation. If an angle is in standard position, are theta and negative theta never, sometimes, or always reflective across the x-axis? So we're just going to investigate all the different types of angles that we know. We'll start with acute angles. I will do my positive angle in blue and my negative angle in red. You ready? So I'll start with this first graph here. So on this graph, we're going to draw an acute angle theta. So that would be a rotation up. Let's say we just do like 60 degrees-ish. Pretend we did 60 degrees. So that's positive theta. And we do a negative theta in the same standard position. That's a rotation of how far? Nope, 60 degrees and negative 60 degrees. No, it just has to be in standard position. Theta is 60, so negative theta is negative 60. That is opposite signs. Here's my question. Are they reflective across the x-axis? Yes? Okay, so we're going to say yes to the acute angles. Okay, so far, maybe always reflective. Let's try another type of angle. What other kinds of angles do you know? Obtuse. Okay, so how about we do 3 pi over 4? So positive 3 pi over 4 radians and negative 3 pi over 4. So that's just a quadrant and a half. So if we go in a rotation in a negative motion, a quadrant and a half. So there's negative 3 pi over 4. So there's an obtuse angle and it's opposite. Are they reflective across the x-axis? So for obtuse, we would say it's also true in that circumstance. What other kind of angles do we know about? Right angles? Okay, so we'll do a positive right angle, pi over 2, and a negative right angle, negative pi over 2, reflective across the x-axis. Yes or no? Okay, so right angles are also reflective. The opposite, pi over 2 and negative pi over 2. What other kind of angles do we know? There's 2 more types that we could study. What's greater than obtuse? Straight? Okay, let's do a straight angle. All right, so a straight angle would be, shall we do 180? Right? Yes. And a negative 180. Is that reflective across the x-axis? I want you to think of the x-axis as a mirror. Yes. Yeah, absolutely. So even in that circumstance, it's just that both of those angles are actually touching the mirror, but they're touching mirror from opposite sides. One more other type. So we know acute, obtuse, right, straight. There's ones that are greater than straight. They're called reflexive. So let's do a reflexive angle. Like say let's do 7 pi over 6, which is 180 degrees plus 30 degrees. So I'll just write in blue, 7 pi over 6. So that's 2 quadrants and then another 30 degrees, or another pi over 6. So if we go in negative way, negative rotation, 1 quadrant, 2 quadrants, and then another 30 degrees, or another pi over 6, negative 7 pi over 6. Okay, so even our reflexive angles are reflective. And if we rotate around and around and around and around and around, because trig functions are periodic, every 2 pi, they repeat over and over again. What conclusion, or what can we say about angles in standard position if they're opposite, if they're opposites? One's a positive and one's a negative. Are they never, sometimes, or always reflective? Always. So theta and negative theta, always reflective across the x-axis. Excuse me. I hate when I cough on video. Okay, so let's extend that out. So remember what our goal is. Our goal is to determine which of our functions are odd or even. So what did that study have to do with anything in regards to odd or even? Well, we have to employ some other things that we know. So let's talk about all our functions. So what generalization can be made about the values of the 6 trig functions of angle theta and angle negative theta as a result? So we'll study them with their reciprocals. So I'll start with the sine function. So, and cosecant. So sine and cosecant of theta and negative theta. So what do we know about their values? Well, here's some things that we've learned so far. That sine and cosecant are positive in your upper quadrants, right? And their values are negative in your lower quadrants, right? A smart trig class. We have our mnemonic to help us remember that. So positive in your upper quadrants and negative in your lower quadrants. So if I put theta up here, sine is positive, right? If I put negative theta down here, sine has a negative value, right? So sine is positive, and reflected across the x-axis it is negative. What if I put it over here? Theta and negative theta. Still opposites? So let's draw a generalization about sine and cosecant. If their angles are opposite thetas, a positive theta and a negative theta, what can I say about their values of positive theta and negative theta? They're opposites, right? So here's my conclusion. The values of sine or cosecant of theta and negative theta are opposites, leading me to come to the conclusion, therefore, that sine and cosecant are odd functions. We will see a really good representation of that tomorrow when we graph. Visually, you'll go, oh yeah, that's definitely odd. Okay, we're going to do 2 more. So let's go and look at cosine and secant of theta and negative theta. Notice that I keep putting parentheses around negative theta. Really need to tuck parentheses around any negative radians or degrees when they're being preceded by a function, a trig function. Okay, so we'll go through that same idea and see if we can make a generalization about cosine and secant. So what do we know about the signs of the values of cosine? On the right side, on the right quadrants, cosine is positive, right? And on the left side, cosine and secant are negative. So reflective across the x-axis, their signs. Cosine is positive, and then on the other side of x, that's positive, or cosine is negative, and on the other side, it's negative. So if we were to draw theta up here, and theta down, negative theta down here, what could I say about the cosine values? Right? Positive equals positive. And if they're over here, and theta is represented down here in negative theta, both signs are negative, right? So what could our conclusion be? The values are equal. Yeah, the values of cosine or secant of theta and negative theta are equal. They're the same. So what conclusion do you think I'm going to draw in regards to even or odd? When I plug in a positive, I get the same thing as when I plug in a negative, right? Whereas over here, if I plug in a positive or I plug in a negative, I get the opposite of the positive, which is how it works. So let's do the last one. Ready? Tangent, cotangent, and I'm sure at this point you don't need me, but for people that aren't here today, I'm going to go ahead and finish out this example. So the tangent or cotangent of theta and negative theta. So again, we're going to use our quadrants. And what do we know about tangent and cotangent's values? When are they positive and when are they negative? Quadrant 1. Quadrant 2. Quadrant 3. Quadrant 4. So across the x-axis, they're the same or they're opposite? Opposite, right? So if I put theta up here and negative theta down here, their values are opposites, right? Instead of the same. And on the other quadrants, it's the same idea. Theta, negative theta, their signs are opposite. So the tangent of negative theta is equal to the negative tangent of positive theta. They're opposite. So our conclusion again, are the values of tangent, cotangent of theta and negative theta are opposites. Therefore, odd. Therefore, tangent and cotangent are odd functions, is what I'm getting at. Okay? Questions? You need clarifications? So you see me relying on things that we've already talked about to support my conclusions. Okay, let's talk about the even and odd identities. So I'm about to talk to you about those. So recall I had you write these down, and I'm doing this for the people that weren't here. The definition of an even function is this. The f of negative x is the same thing as the f of positive x. But now we're talking in theta instead of x, right? It's just a different variable. So we've just decided that cosine of theta and secant of theta, if they're reflected across the x-axis, their signs are the same. Their values will either both be positive or they will both be negative. So cosine and secant are even functions. So we can say that cosine of negative theta is equal to the cosine of positive theta. And the secant of negative theta is equal to the secant of positive theta, based upon what we know about their placement on a coordinate plane. And then our definition of odd function, if you recall our conversation we just had like 3 minutes ago, well, 3 minutes before we started notes. If I plug in a negative x in an odd function, I plug a negative x into the function, I get out the opposite output. I get out a negative. If I plug in a negative, my output's negative or not negative as much as it is opposite. Okay, so we decided that the sine of negative theta right here is equal to the opposite of the sine of positive theta, right? Because their signs are opposite. So the sine of negative theta is equal to the negative sine of theta. Really important to remember the difference between these. Same thing for cosecant. And we also discovered the truth in regards to tangent. When we had negative theta, it was the opposite of positive theta. That's what we found out. So tangent of negative theta is negative tangent of theta. And negative cotangent of negative theta is equal to negative cotangent of theta. So we've pretty much explained through illustration which are even and odd based upon their value outputs. When is tangent positive or negative, like that. So now we're going to put it into practice. Now you'll notice in my instructions here I said the even and odd identities. This is my preferred name for these identities, but our textbook calls it the formula for negatives, which is, some textbooks call it that, but I know in calculus your teacher's going to call it even and odd identities, so we're going to stick with that nomenclature. But the instructions say on your homework to use the formula for negatives to find the, here's important, you're listening to the words coming out of my mouth, the exact value, which means I'm probably wanting the square root version and not the decimal version that your calculator is going to give you. So either you're drawing a picture of your unit circle, you're looking at your unit circle, or you're using your exact trig values paper that I gave you. So we're going to use the formula for negative, or the odd even identities. So here we have the sine of negative pi over 4. Well, I'm just going to draw a little sketch of that over here. So negative pi over 4 is right here. Negative 45 degrees. And what do I know about the sine of that? Here's what I know. Down here, my sine is negative, and my second coordinate is negative. And it's the square root of 2 over 2. So that it should be negative square root of 2 over 2. That's what it should be, based upon my picture and based upon what I know about a negative pi over 4. But it says use the formula for negatives. So here's what we talked about. The sine of negative pi over 4 is equivalent to what? The negative sine of pi over 4. And when your theta, whatever it is in, or your degrees or your radians is a fraction form, put parentheses around it. Okay, so that was an odd ID. So OID is what I'm going to write down as a little explanation. And then what I'm going to do is I'm going to find the sine of pi over 4, which is up here. And the sine of pi over 4 is the square root of 2 over 2. Truth? So we're just going to use substitution. The opposite of the square root of 2 over 2 is negative square root of 2 over 2. So I use substitution by plugging in its exact value of pi over 4, the sine of pi over 4, and then I use simplification, the opposite sign. So this is what I'm asking you to do. Let's do the next one. Cosine of negative 5 pi over 6. Let me get a fatter eraser here real quick. Maybe I'm going to move this out of the way. Maybe. Oh, well. I'll just draw the picture over here. Okay. So 5 pi over 6 is in quadrant 2, right? 150 degrees. So negative 5 pi over 6 is over here. Here's what I know about the cosine in this quadrant, in negative 5 pi over 6. Here's what I know about the cosine of positive 5 pi over 6. So their cosines are equal. So positive 5 pi over 6 is equivalent to the cosine of negative 5 pi over 6. Truth? So I can replace cosine of negative 5 pi over 6 with cosine of positive 5 pi over 6. They are the same. Their values are the same. And then you're going to either go and draw yourself a 30, 60, 90 right triangle, use your unit circle, or use your trig value sheet. What's the cosine? Square root of 3 over 2? Check me. Negative square root of 3 over 2. Use your trig value sheet. What's the cosine of 5 pi over 6? I know it's negative. Negative square root of 3 over 2 is correct. Okay. All right. Tangent of negative 120. What quadrant is that in? Negative 120 degrees. Isn't it quadrant 3? Yeah. So it's right here. And what do we know about tangent down here? Its value is positive, right? So it's negative 120 degrees, and we know tangent is positive because it has a negative opposite and has a negative adjacent. Adjacent, negative divided by negative, positive. So the tangent of negative 120 is equivalent to the negative tangent, or the opposite of tangent of positive 120 degrees. So using your trig function sheet, what's the value of the tangent of 120 degrees? No. Negative, what? No. Isn't it? Wow, you guys didn't fill out your sheet very good. Isn't it negative 3 over square root of 3? No? I feel like it is. And I'm going to wait for you. Otherwise, I'm going to draw it. So 120 degrees. So that means this is a 60-degree angle. So this is 1/2. This is the square root of 3 over 2. And this is 1. And tangent is opposite over adjacent. So the square root of 3 over 2. Square root of 3 over 2. So it's a negative square root of 3 over 2. And if you don't have that on your tangent of 120, you need to fix it. Shh, bring it back. And we have the opposite of negative square root of 3 over 2 is the square root of 3 over 2. Okay. All right. Let's move on. Cotangent of negative 225. So what's the rule? Cotangent's even or odd? Odd. So the cotangent of negative 225 is the same as the negative cotangent of positive 225 degrees, or the opposite. So let's take a look at the cotangent of 225 degrees. Well, if I draw that picture, 225 degrees is over here, and it's halfway through quadrant 3. So I'm pretty sure tangent and cotangent are positive, and cotangent is 1. Yeah? So negative and cotangent of 225 is 1. So the opposite of 1 is negative 1. Okay, you guys do secant of negative 30. Go ahead. I'm going to erase some things. And then I'll write the answers. And also do the cosecant of negative 3 pi over 4, please. Use your trig value sheet. Oops. Okay. So for secant of negative 30, it's even. So it's equivalent to the secant of positive 30. And the secant of 30 per our trig values exact is 2 square root of 3 over 3. And then with your cosecant of negative 3 pi over 4, this is an odd identity, so it's equivalent to negative cosecant of 3 pi over 4, or the opposite of cosecant. And cosecant of 3 pi over 4 is the square root of 2. And so the opposite of the square root of 2 is negative 2. And it's just going to require some practice. I will tell you this. It would probably really benefit you to actually draw the units. We'll draw the angle on a coordinate plane and then drop in a vertical line on your angle. Use the reference triangle and use your 30, 60, 90 rules or your 45, 45, 90 rules. That would be so beneficial because then you're not always referring to your unit circle paper or your exact values paper. All right, last thing. Back to verifying identities. Ready? Here we go. Verify the identity by transforming the left-hand side into the right-hand side. Here's my tip. I have now introduced the even and odd identities. Step 1 should be to always look for the even and odd identities. Always. Step 1. If you have a negative theta, deal with it. Apply the even or odd identity, and then decompose and do all the other things that you know how to do. Use your Pythagorean reciprocal quotient identities. Use your order of operations, all the things you know how to do. So let's start with the first one, which is just a two-step process here. So we have sine of negative x over cosine of negative x somehow equals a negative tangent of x. So my advice, remember, apply your even and odd identities. So I'm going to replace the sine of negative x with negative sine of x. And I'm going to replace the cosine of negative x with cosine of positive x, right? Because sine function's odd, cosine function's even. Okay, we just talked about that. All right, so equals negative tangent of x. So let's write just a quick description over here because you have a new notation. So what I'm just going to do is odd or even identity, O or E. And since we used both of them, I'm going to list them all. If it was just an odd identity, you do OID. If it was just even, you do EID. Okay, now what? Come on, you should need me now. Now reciprocal. It's a quotient identity, right? The negative sine over cosine is the negative tangent, is it not? Okay, but there's two things happening here because the first thing I'm doing is I'm doing negative divided by positive is negative. So I'm going to use my blue pencil as a different thing that I'm doing. I'm simplifying. I'm dividing positives and negatives. And then I'll replace sine of x over cosine of x with tangent of x in red. So those are two different things that I'm doing without writing two other steps. So over here off to the side, I'm going to say simplifying, negative divided by positive. And then in red, I'm going to say that I applied a quotient in red. I applied a quotient identity. So that was a pretty good indicator of how to use your even and odd identities. Let's take a look at the next problem. So here you have the tangent of negative x times the sine of negative x plus the cosine of negative x equals the secant of x. So we have two terms on the left and one term on the right. So somehow we got to go from 2 to 1. I know. Wake up. Here we go. We're almost done. So first I need to deal with all these negative angles. I don't want negative angles. So let's write their equivalent values. P.S. This is, I said this. That means multiply. Okay. So we're going to replace tangent of negative x with negative tangent of x times sine of negative x is equivalent to negative sine of x. And notice that I put it in parentheses. It's just proper. Okay. Plus cosine of negative x is equivalent to cosine of positive x equals secant x. So what did I use there? What properties? Odd and even. I used both of them again. Okay. So from here on out, you shouldn't need me, but we'll work it together because there is something I want to point out that I noticed on the last test. What shall we do next? What is your advice? Decompose? I like it. So let's decompose tangent into sine and cosine, right? So the negative sine of x over cosine of x times negative sine of x. And if you don't mind, I'm going to put that over 1 because I'm planning to multiply those two things. So they need to be fractions. And then I'm also going to write the cosine of x over 1 because at some point I'm going to want to add those two numbers together. Equals secant of x. So here I decomposed. And I used the quotient ID to decompose. All right. So here's the thing I wanted to mention. I noticed when I graded the last tests, a lot of people really struggled with this next thing. Here I have two operations. I'm trying to simplify these three things into one thing. Now, since I have multiplication and addition, I have to follow the order of operations that states that I always multiply before I add, unless there's addition in parentheses or something. And so this is the first thing I have to do. So over here, I'm going to write order of operations. Multiply first, because I noticed that people were struggling. Maybe because it was in trig notation instead of just regular numbers. It was a little confusing. We need to clean that up. So let's multiply those two together. So negative sine of x times negative sine of x is sine squared x over cosine x plus cosine x over 1 equals secant of x. All right. So that was the order of operations. Multiply first. Now what? Common denominators. If you don't mind, I'm going to go ahead and just use a secondary color on the same line because we're running out of space. Right? So secondary, I'm going to do common denominators. So Jill's denominator says this one wants cosine of x over cosine of x. And we'll simplify. Okay. So can we add now? Since they have common denominators? So that would be sine squared x plus cosine squared x all over cosine of x equals secant of x. Oops. All right. So what did we do? 2 to 1. We did order of operations, add second. That's what we did. We combine like fractions. Now what? What do you see? Look. Pythagorean identity. Sine squared x plus cosine squared x equals 1 over cosine x. This should become really apparent now that this is a true statement. So we used a Pythagorean identity there. And lastly, what do we know? 1 over cosine is equivalent to secant of x equals secant of x through what? Reciprocal identity. And there it is. There it is. So your homework's on Canvas, and I will tell you that at the top of the page, and it's like 3 pages long, but at the top of the first page are the exact problems that I'd like you to do for this specific set of practice problems. So check that online.